Thank you very much for introduction. Yes, I'm going to talk about the new design approach for stream ciphers. So yesterday we've heard all this very interesting talk about the current challenges in the lightweight cryptography standardization and given by Meltem from NIST. And as far as I understood, they are not very much interested in the stream ciphers. And in fact, this is understandable, because even the lightweight stream ciphers, in fact, with respect to the area size, they are comparable to IAS. And in our work, we actually tried to solve this problem, or at least to make a step forward. Yeah, this work is done together with Frederick Armknecht. So this is a short outline of my work, and so I will quickly explain what actually the problem is. We'll explain how we solve this problem, and we'll demonstrate that our approach works on the concrete stream cipher that we propose, and we'll sum up the paper. So I will not talk a lot about why we need lightweight crypto. It is required for wireless sensor networks, body area networks, RFID tags, and when all these devices need to encrypt the information, the lightweight ciphers are used. And as you can see from the paper, so these are some of the modern lightweight ciphers. In the first part, you see the block ciphers, and in the bottom part, the stream ciphers are presented. So, as you can see, the area size for the stream ciphers, even for those which are considered to be lightweight, is in fact much higher compared to the lightweight block ciphers. And it's comparable to IAS. So, as far as I know, we have already the implementations of IAS which require 2400 gate equivalents. But the advantage of the stream ciphers is, of course, the throughput. And the question is it actually possible to construct the stream ciphers which still provide the same level of security but require less area? Why this difference actually come? Where does it come from? And there exists a common rule of thumb that says that the stream cipher internal state size should be at least twice the security parameter. And actually it leads to the situation that in order to implement such a cipher, we need at least two times the key size number of the memory gates, which are the most costly parts with respect to the area size and the power. I will shortly explain why this actually happens, where this rule of thumb comes from for the stream ciphers. Most of the stream ciphers are based on the key stream generators, and we usually consider two parts, the initialization phase, two phases, the initialization phase and the key stream generation phase. And in the initialization phase, given the EV and the key, using the initialization function, we get the initial state, and then during the key stream generation process, this state is continuously updated at every round, and the key stream is produced. So as you can see, the key is only used in the initialization phase, and in fact, it is not involved in the key stream generation phase directly anymore. And the time memory trade-off attacks aim to invert a function. So basically, given an output of the function, the goal is to find the input, and the two phases are considered. In the pre-computation phase, the attacker takes some values and pre-computes the outputs of the functions for these values. And in the real time, given function outputs, the attacker checks if any of them is covered by this or that table. And these attacks are very efficient against the key stream generation. And this is due to the following reasons. So in fact, the attacker does not require to it is not necessary to invert the function key to the output. It is only sufficient to invert the function state to the output. And in fact, knowledge even of only one state allows the attacker to find all the succeeding or preceding keystream bits, or even by applying the update function several times, this or forward or backwards, and even to come back to the initial state, then invert the initialization function and to find the key. So the BG attack was actually the first attack which uses the multiple data for breaking the keystream generators, and it was further improved, but the main principle remains the same. So the goal of the attack is to find only one of the internal states. So the search space is equal to 2 into the power of state size. And in the online phase, the attacker simply chooses m random internal states, precomputes their outputs, and stores this in the table. So the m is also equal to the precomputation time. And in the online phase, given a certain keystream, the attacker selects d possible keystream segments and checks if any of these segments is covered by the table. So it's a very straightforward approach. So by birthday paradox, these two sets will intersect if their sizes is equal to the search space size. So in fact, in order to have a high probability of this attack, the memory size multiplied by the time should be equal to 2 into the power of the internal state size. So, and if you have t which is equal to m as a particular point on this trade-off curve, then we have the situation that in order the attack to be successful, the time and memory should be equal to 2 into the power of half of the internal state size. Basically meaning that the internal state size needs to be at least twice the key length. And the overall question is it possible to somehow avoid this rule of thumb using this design? And the answer is no, this attack is generic. However, is it possible to tweak the stream cipher design to avoid this attack? And we think yes. So now I'll explain what we propose. So first of all, please take a look on what the keystream equivalent states are. So the two states are said to be keystream equivalent if, in fact, if one can be obtained by another by applying the update function several times to it. And the keystream equivalent class contains all such states which can be obtained from each other by application of the update function. So for most of existing keystream generators, the set of all states is in fact equal to one equivalent keystream equivalent class. However, this is not necessarily true, and for arbitrary keystream generator, this set of states in fact should be a union of several keystream equivalent classes. So suppose we have several keystream equivalence classes, and the attacker is given some keystream based on a state, st0. So in order to apply the time memory trade-off attack, the keystream equivalent class st0 has to be considered either during the precomputation or the online phase. Hence, the attack will be a union of time memory trade-off attacks, one for each of these equivalence classes. And if we have L equivalence classes, then at least L attacks are required. And if this number is L is bigger than key space size, then the time effort is not less than the exhaustive key search. So how can we actually construct the ciphers with several keystream equivalent classes? So what we propose to do is to fix one part of the internal state of the keystream generator. So if we have one part which is fixed, then it cannot be changed, and then two values of this fixed part will result into two different equivalence classes. Therefore, this number L will be equal to 2 into the power of this length of the fixed part. But of course, it doesn't make sense to simply fix one part of the state. Instead, we could actually use the secret key, consider the secret key as a part of the internal state. And this can be done by simply directly involving the key into the update process. So will it still be a stream cipher? So if we come to the handbook of applied cryptography, and we will see that such construction is covered by the definition. So what we have, instead of a long internal state, we now have internal state and the key. And we gain in two things. So first of all, storing a fixed value can be realized with significantly less gate equivalence compared to register. Therefore, when the key is fixed, one can save area. In fact, the same principle was used in Ctan. And the second observation is that it seems that the resistance against time memory trade-off attacks now depends only on the key size. And this actually allows us to construct the stream ciphers with a very short internal state, but of course sufficiently long key. And actually we tried to prove this paradigm by designing a concrete stream cipher. So our goal was to show the feasibility of this approach for reducing the state size, and we decided not to start from the beginning, but to take already some existing established design, which should be lightweight, scalable at least to some extent, and which has to be already well analyzed. So we selected grain 128A for this purpose. So grain 128A, in fact, it also can use the authentication part, but it is not important for us, so I do not discuss it in my talk. So grain 128A is composed of the NLFSR and LFSR, where the LFSR output is fed into the NLFSR input, and several bits of the NLFSR and LFSR go into the output function. So what we did with the new design, first of all, of course, we reduced the state sizes for the NLFSR and the LFSR. In our cipher, which we named Sprout, we use 40 bits registers. We also involve the key into the NLFSR update function and involve the counter into the update process. The counter helps us, actually it is needed for grain anyway, in order to count the number of bits required for the initialization phase, and we simply use it to make the period longer. And of course we had to modify the functions as long as the registers are shorter now. So this is the structure of the proposed stream cipher. So as you can see, the registers are 40 bits each now, and we also use the round key function, where at every cycle the certain round key is selected and is added into the NLFSR update. We also use 1 bit of the counter in the NLFSR update, and the functions are modified. So in all other aspects, the Cipher is similar to Grain. So we have called it Sprout because Grain already has some kind of plant-related name, but also we somehow seed the key inside the internal state of the Cipher, and we hope that it sprouts fast among the internal state. For the round key function, actually we had many different possibilities of how to construct the round key function, but we decided to stay for the beginning as simple as possible. So we reuse counter for this function, and in fact during the clock cycles, okay. So at every clock cycle, we select one of the key bits using the counter. For the first time, we select every key bit for the clock cycle 0 to 79. And at each of the following clocks, we select this bit with a probability 1/2. So in fact, only when these values are, the sum of these values is equal to 1. Here you can see the implementation results. As you can see, Sprout requires significantly less area size compared to the other existing lightweight stream ciphers, and has the advantage of the throughput. And in fact, it is already comparable with the lightweight block ciphers with respect to the area size. Unfortunately, I don't have time to explain the security analysis of Sprout. However, as I said, we try to stay as simple as possible. The two main issues are, of course, when we try to make the internal state size shorter, first of all, the period of the sequences becomes shorter, and also guessing determinant text becomes easier. So in fact, we have already received a few indications of weaknesses found in Sprout, and at the moment it seems that the round key function has to be more complicated. However, for the moment, no of the time memory trade-off attacks were found. So our contributions are this new approach in stream cipher design, where the update functions involves directly the key. So our hope that the internal state size can be significantly reduced. So to prove this concept, we proposed a new stream cipher, which in fact is considerably smaller compared to the other existing lightweight stream ciphers. So the open questions would be is to further investigate the security of Sprout. It's already clear that we need a better, more secure round key function. But with Sprout, we tried to stay relatively modest while taking the state size to be 80 bits. In fact, we don't see any reason why we could not reduce the internal state even further to be, let's say, 50 bit. And the question is if we can construct a new stream cipher with, let's say, 128 key bit and with only 50 bit internal state, which would provide the 128 bit security. So this is it. Thank you very much for your attention.
Any comment or question for Vasily? Yes. So you didn't mention how you load the IV to the state, or how you initialize the NFSR and the LFSR. Did you? So if you have grain 128 has a 96 bits of IV, I believe, but you don't have any space to load the IV. Do you use IV?
Well, actually, we have the 80 bits for the key, and if I remember correctly, we have, I think, 67 bits for the IV. Yeah, so the IV is loaded into the NLFSR and the LFSR. Again, a few bits of the LFSR are initialized by ones, and then we have 300.
All ones? They are initialized with all ones?
And 0 at the end. And then we clock 320 times for the initialization phase. I mean, I didn't stop too much in detail because of the time.
Mm-hmm. Okay,
but
thank you.
Thank you very much for your question. Now I had time to explain this.
Thank you. On the current slide, we see that the counter you're using is marked with yellow color, and I think that in this construction it effectively becomes a part of the state. So what is the size of the counter? Does it contribute to the state size?
Oh, well, actually the size of the counter is 9 bits. I mean, yes, we could consider as a part of the state size.
Thank you.
So if we change the key, I mean the key can be changeable, then what will be the area cost in this case?
Well, actually, we made such experiments, and I mean, as long as we took the NLFSR and the LFSR to be 80 bits altogether, and if the key is 80 bits, so in fact it will require approximately the same size as grain, which requires 160 bits for grain 80, which requires 160 bits for storing the internal state. And our experiments confirmed this. So in fact, we have just a few gates more compared to grain 80. Yeah, I can. So it was about 1200 gate equivalents. But actually this construction allows to even further reduce the internal state. So even if we have the key changeable, this should also allow for the construction with a shorter internal state size.
Did you look for analysis of grain for some attacks which may be more effective to your design? You know, to modify the analysis of some attacks to grain to this kind?
Well, actually, at the moment, it seems that actually guess and determine attacks are the most efficient against this construction, because the internal state is already very short, and if we guess part of the state, which can usually be done more efficient compared to the exhaustive key search, then for this reason we actually need really good key around key function in order to hide the key as good as we could. But it seems that the function that we use is not secure enough, and we already have some indications for this.
Okay, so let's thank the speaker again.
Thank you.